Hi, welcome to one and all. Next, we will be discussing the new module that is quadratic residues and quadratic reciprocity law. In this, we will be mainly talking about the congruence and the quadratic residues. And before that, let us recall what is congruence modulo. I hope you have already learned about congruence modulo. The congruence modulo is defined as given an integers a, b, m with m greater than 0. We say that a is congruent to b modulo m, and that is written as a is congruent to b mod m if m divides a minus b. That is, whatever is here, a minus b, the difference between these two should be divisible by m. The number m is called the modulus of the congruence. Okay, now let us see what is polynomial congruence. An integer x satisfying a polynomial congruence f of x congruent to 0 mod m, where f of x are polynomials with integer coefficients, is called the solution of the congruence. That is, this is called the polynomial congruence. That is, f of x is congruent to 0 mod m. And if we can find an x which satisfies this congruence, we say that that is a solution of this polynomial congruence. We already know that you have already studied these things. If x congruent to y mod m, then f of x is congruent to f of y mod m. So every congruence having one solution has infinity many. This, if it has one solution, then it has many solutions. Now let us come to the quadratic residues. In earlier module, you have already studied the problem of solving a congruence, polynomial congruence, that is f of x is congruent to 0 mod m, can be reduced to a polynomial congruence with prime moduli plus a set of linear congruence. This is what you have studied in 5th chapter. Now we will be studying the quadratic congruence of the form x square is congruent to n mod p. X square is congruent to n mod p, where p is odd prime and n is not divisible by p. Here note that p is an odd prime and n is not congruent to 0 mod p. That means n is not divisible by p. Since the modulus is prime, we know that one has at most two solutions. It's a quadratic one, so it has at most two solutions. Therefore, if x is a solution, so is minus x. Hence, the solutions is either 0 or 2. But we need to prove this in detail. It's simply can leave it as an exercise, but here I will prove how this becomes either 0 or 2 solutions for this quadratic congruence. Let us see the question. Show that the quadratic congruence in equation 1, that is x square congruent to n mod p, where p is an odd prime and n is not congruent to 0 mod p, as exactly 0 or 2 solutions. Also, we will prove that the only solution is x equal to 0 if n equal to 0. So let us begin. Now we already say in the statement is given that n is not congruent to 0 mod p. That means p does not divide n. So that is what p does not divide n. To show that 0 or 2, there are 0 or 2 solutions, that is, there is no solution or at least only 2 solutions. We first show that there is at least one solution. Suppose there is at least one solution m. Now if m is a solution, we know that this m should satisfy this equation, x square is congruent to n mod p. So clearly m is a solution, so m square is congruent to n mod p. If m square is congruent to n mod p, then minus m square is also congruent to n mod p. So minus m whole square is congruent to n mod p. So now we have to claim that this m and this minus m are two distinct solutions, which is not the same solution but the distinct solution. So now we are going to prove that. If they are not distinct, then it means that they are same. That is, m is congruent to minus m mod p. That means m, this minus m can be taken to this side, so m plus m is divisible by p. It will become m plus m is divisible by p. That is 2m is divisible by p. That is p divides 2m. P is an odd prime. It is given that P is an odd prime. That means odd means it does not contain a number 2. So P does not divide 2. That means that P should divide M. So P should divide M. That what is the meaning of that? P divides M means M is congruent to 0 mod P. That means M square is congruent to 0 mod P. So if M square is congruent to 0 mod P, and what is M square? M square, so M square is congruent to 0 mod P, then clearly N is congruent to 0 mod P. But we have already assumed that N is not congruent to 0 mod P. So that is a contradiction. P does not divide N. So our assumption was wrong. We said that M and minus M are not distinct. That is wrong. So M and minus M are distinct. That means M is not congruent to minus M mod P. Thus we have two distinct solutions. Since a quadratic equation, mod P has at most two solutions because it's a quadratic form. So it is quadratic. That means only two solutions will be there. So we have got that two solutions. So there are exactly two solutions. That is a proof. Now if x, the next part of the question is prove that only solution is x equal to 0 if n equal to 0. That part we have to prove. If x equal to 0, then clearly x square is also congruent to congruent mod P. That means x is a solution, so x square congruent to 0 mod P. And if conversely, if we assume x square is congruent to 0 mod P, then P divides x square. That means P divides x, and hence x is congruent to 0 mod P. So that completes the proof. Now let us come to the main definition. Here, if the congruence, that is x square is congruent to, that is n1, x square is congruent to n mod P. X square is congruent to n mod P. As a solution, we say that n is a quadratic residue mod P, and we write nRP. That means n is a residue of residue mod P. N is residue mod P. And if one has no solution, no such solution, we say that n is a quadratic non-residue mod P, or n is not a quadratic residue mod P, or n r bar P. So now in this section we will be discussing mainly two problems. One is that given a prime P, determine which n are quadratic residues mod P and which are quadratic non-residues mod P. That is, if we are given a prime number P, we want to determine those n's which are quadratic residue mod P and those n's which are not quadratic residue mod P. And another question is that given n, determine those primes P for which n is a quadratic residue mod P and those for which n is a quadratic non-residue mod P. That is, first part is we have to find n's which are quadratic residue mod P and and those n which are not quadratic residue mod P. In the next part we will be finding those primes which n is a quadratic residue mod P and those primes which n is not a quadratic residue mod P. So let us see an example where we can find an example of how to find the quadratic residues mod a prime number. So if P is a prime number, how to find the n's. So find the quadratic. Let us look into this question. Find the quadratic residues modulo 11 and the quadratic non-residues modulo 11. This is a question. So we have to find the residues mod 11. So what you have to do is simply we have to solve that question. That is x square is congruent to n mod P. This is what we have to do. So we have to take the quadratic residue, means we have to take the square of those numbers and which is congruent to that number, and that n's are what we have to find. So first what we will do is to find the quadratic residues modulo 11, we square the numbers 1 from 1 to 10. That is the numbers just below this number. This is a prime number, so all the numbers are, we have to take 1 from 1 to 10 and reduce modulo 11. That means we have to find the squares of these numbers and divide it by 11, and we have to find the remainders. That is what the n's will be. So remainders obtained are called the quadratic residues mod 11. So these are the numbers x 1 2 3 etc up to 10. X square is 1 squares of these numbers. That is 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. So but 16, when you take the remainder, it is 5. Here these are the remainders, because when you divide 1 it is 1, when you divide 2 it is 4, and 3 it is 9, 4, and 5 it is 25, square is 25, and the remainder is because when you divide it by 11 you will get the remainder 3. And the remaining numbers, please note the remaining. 6 is 36, when you divide it will be 3. 7 is 49, when you divide it will be 5. 8 is 64, when divide it will be 9. 9 when you divide it will be 4, and 10 when you divide it will be 1. But you can see this, only half the numbers you have to evaluate, because the remaining half is just opposite to this same. If this is a k, you have to divide only up to the number k. The remaining number is something like p minus k. This is, if this is p, 11 is p, then it is p minus k. See, p minus k, the remainder is same. See, for 11 minus 6 it is 5, so it will be, the remainder is same as that of 5. And 11 minus 7 it is 4, so it is remainder of same as 4. So all the it will be in the reverse order. So hence we could see that 1 square is 1, 2 square is 4, 3 square is congruent to 9, 4 square is congruent to 16, 5 square is congruent to 25, which is 3. So we need only find this first half. The second half is not necessary, because 6 square is minus 5 square, which is 3, 7 square is minus 4 square, which is 5, 8 square is like that, 10 square is minus 1 square, which is 1. Thus the quadratic residues modulo 11 are 1, 3, 4, 5, 9, because see here it is 1, 4, 9, 5, 3. So the same numbers are repeating. So 1, 3, 4, 5, 9. These are the quadratic residues modulo 11. And the remaining, all the remaining numbers between 1 and 10 are the non-residues. That is 2, 6, 7, 8, and 10 are the quadratic non-residues. If it is a residue, so 1 is quadratic residue, so 1 r 11. 3 is a quadratic residue, 3 r 11, like that. And 2 is not quadratic residue, so it is 2 r bar 11, 6 r bar 11, like that. So I hope you have understood this concept properly. In the next session we will be discussing one more example. I hope if you have any doubt, you just mail me or send me a message. Thank you very much for your patience.